Okay, so this here I'm looking at filling in the table with signs of f prime and f double prime on the indicated intervals. Okay, so the first interval I'm looking at is from -10 to -8. So on this interval, I can see that my graph is increasing, so f prime is positive, and my graph is concave down, so f double prime is negative. Between -8 and -6, I can see that my graph is decreasing, so f prime is negative, and it's concave down, so f double prime is also negative. Between -6 and 0, I don't really know why it says -0 there. I think that's a typo. But between -6 and 0, my graph is increasing, so that means f prime is positive, and my graph is concave up, so f double prime is also positive. From 0 to 4, so x equals 0 to x equals 4, f is increasing, so that means f prime is positive, but f is concave down, so f double prime is negative. From 4 to 8, I can see that my function f is decreasing, so f prime is negative, and it's concave down, so f double prime is also negative. And from 8 to 10, my function is decreasing, so f prime is negative, and it's concave up, so f double prime is positive. The next thing says to list the coordinates of all critical points. And so critical points here would be where f prime is equal to 0 or where f prime does not exist. So what are the places where the derivative is 0 or doesn't exist? That would be here, here, here. And so when it says the x coordinates, I want to list the x coordinates of those critical points. So that is x equal -8, -6, and +4. And the next one says I want to list the coordinates of the inflection points. So inflection points are going to be x values where the second derivative changes sign. So it looks like here and here. So that is at -6, it changes concavity. It changes concavity at 0, so it goes from concave up to concave down. It changes concavity at positive, and at x equal 8, it changes from concave down to concave up. But here it doesn't say just the x coordinates, it says the coordinates. So maybe I should write out all the points there. So it looks like the point at x equal -6 is -6, 1. And the y value at x equal 4 is 6. And then the x coordinate that goes with 8 is, looks like maybe 1.5. Okay. So those are the points there. Okay, so the next one I'm just supposed to compute the derivatives here. So for this one, you might notice that I have a composite function. So I have a function inside of another function. I'm just going to put some parentheses up here around this cosine of theta just to emphasize that this is a composite function. So when I find f prime, I need to take the derivative of the outside function first. And I want to leave the inside part alone. 4 to the cosine theta times the natural log of 4. So that's the derivative of the outside part, 4 to the x, 4 to the something. And then I want to multiply that by the derivative. So the derivative of cosine theta is negative sine theta. And so once you've taken the derivative of the inside function, then you're done there. Okay. So for the next one, I want to find the derivative, but what you might notice about this function is that it's a product of two functions. So when I have a product of two functions, I need to use the product rule to find the derivative. So dy dx is going to be equal to, and I'm just going to go ahead and put my parentheses here and then fill in the blanks. So I want to do the derivative of the first function, so the derivative of e to the x is e to the x, times the second function, secant x, plus the first function, I'm going to leave the first function alone, so that's e to the x, times the derivative of the second function. So the derivative of secant x is secant x tangent x. And you really don't need to simplify that any. You can leave it just like that. And so for the next one, this g of t is equal to natural log of 6 to the t. So again, this is going to be a chain rule because I have a composite function. And so when I take the derivative of a natural log function, first we'll just find the first derivative. When I take the derivative of a natural log function, it's 1 over, and I'm going to just leave the inside part alone, so that's t to the 6th. Then I'm going to multiply that by the derivative of the inside. So the derivative of t to the 6th is 6t to the 5th. I'm going to go ahead this time and simplify because I want to be able to take the second derivative. So if I simplify that, I'll have 6t to the 5th over t to the 6th. So I can divide t to the 5th divided by t to the 5th, and that makes 1. So really what I'm left with is 6 divided by t, which I can write as 6t to the minus 1. Now all I've done there is simplify g prime. I haven't taken the derivative again yet, but I'm ready to take the derivative now. So I can take g double prime of t, and since I have it written this way with 6t to the negative 1, I can just use the power rule to take the derivative again. So I'll have negative 6t to the minus 2 is my second derivative. Okay, so for the next one, I want to take the derivative, and if I notice here, I have the x's and y's are all mixed up, so I'm going to have to take the derivative implicitly here. So here, when I take the derivative of the left-hand side, the derivative of x to the 4th with respect to x is 4x to the 3rd minus, and now when I take the derivative of cosine y, I have to think of this as a chain rule. So the derivative of the cosine part is negative sine, leave the inside alone, then I'm going to multiply by the derivative of the inside, which is dy dx. And then when I take the derivative of the right-hand side, the derivative of sine x is just cosine x. So there's that. And now I want to solve for this dy dx. So what I notice is that the dy dx is multiplied in this term, but not in that term. So I'm going to subtract the 4x cubed from both sides. So I'll leave the sine y dy dx, and I'll subtract the term 4x cubed to the other side. So cosine x minus 4x cubed. And now what's left for solving for dy dx is I can see that I have sine y that's multiplied by dy dx, so I'm going to divide that over. So I get dy dx is equal to cosine x minus 4x cubed divided by sine of y. And there's my derivative, and you'll notice again that my answer for dy dx should contain both x and y, and it does. So